Hi, everybody. Welcome. My name's Steve Napier, and I work for Bodo Wood here in Australia. I'm actually based in Sydney, and today we have two wonderful, very special guests. We've got Daniel Gudsell, who is the marketing director for Bodo, and he's based in Auckland in New Zealand. And we've also got Callum Hill, who is one of the world's, or probably the world's greatest authority on wood modification. So we'll kind of be going in two parts. We'll have a little bit from Daniel first, and then we'll hear a little bit from Callum. So Callum's actually been researching wood modification since 1994, which is quite a long time. He was a senior lecturer in wood science at Bangor University before taking up a post as professor of materials science at the Centre for Timber Engineering in Edinburgh. And he is a researching fellow at the University of Bath and a visiting researcher at the Norwegian Institute of Bioeconomy Research. And he's authored over 180 research papers and 2 textbooks. Wow. Now, what would actually be really good, there's a lot of people from different parts of the world. It'd be good to know where you're from. So I'm in Sydney. I know Callum is in Wales and Daniel's in Auckland. Where is everyone else from? So we get people from Frøslov in Denmark. Oh, wow. That's amazing. We'll start in a couple of minutes. It's going to be quite an intense full webinar. So we'll keep things moving along. But we'll start in a couple of minutes just when the numbers start to even out. Wow, that's amazing. So many places. Now, there's bound to be a million questions. I know I've already started asking Callum all sorts of questions. So put them in the chat box and I'll flag them and then we will answer them at the end, just to kind of keep things straight and so Callum can keep his line of thought going. Do you want to kick us off, Dan?
Yeah. Well, good morning, everyone. My name's Daniel Gudsell. I'm a founding director at Bodo Wood. Right now in New Zealand, it's 9 o'clock at night, so I've got my trusty green tea latte here, and I'm going to power through this presentation. Now, I'll start with probably a quick 10-15 minute talk about Bodo before we pass you on to Callum. A little bit about Bodo. We are a New Zealand family-owned business. We've got distribution in over 35 countries around the world, and we export around 150 containers of our modified wood every month. We've got European stocking distributors, so product on the ground in Europe and, of course, in the UK. You'll notice on my little map there, I've deliberately kept most of the Americas off it, and that's just payback for all those American maps that tend to leave New Zealand off the bottom. Yeah, that's one. For you, Donald Trump. Our business is about providing renewable alternatives to old growth timbers. That's what we do. And it's recognized globally that populations are going to increase and requirements for building materials are going to increase. So it's really important that we think about building materials that are rapidly renewable that we can use to build in the future. And I think people, particularly in Europe now, are recognizing that wood is a great solution for sustainable construction. And we're very blessed in New Zealand that we've got this species called radiata pine that, while it originated from California, grows exceptionally well, and it's a highly productive species. So if you think about the traditional, say, for example, timber cladding used in the UK today, you look at species like Siberian larch and old growth western red cedar, they're beautiful species, but they tend to grow at quite a slow rate. We're talking about, say, and very slow rates, sort of less than 10 times the speed that radiata pine would grow at. And what that means is that they store less carbon on an annual basis. So Callum's actually done a pretty interesting study on this, comparing the relative sequestration rates per species. And I think what Steve's going to do is going to pop that report in the handout section on the right-hand side there. You'll be able to download that report. But the message here is, of course, that if we use rapidly renewable timbers, we can store more carbon quickly and get that out of the atmosphere and bind it up as a wood product. Now, what about coverage and plantation? In New Zealand, we've only got about 7% of our landmass in plantation pine. It's very high yielding, so even 7% of our landmass yields twice the amount of timber that we can actually use, and therefore over half of it's actually exported. And we maintain 24% of our landmass in native forestry. And so we don't go into those forests, we leave those forests alone. The biodiversity is maintained, and we get all of our timber from a very small amount of landmass using a very highly productive forest. And that's why New Zealand radiata pine is a great substrate for modified woods. Another reason it's a great substrate is that a lot of it is pruned. And by pruning, I mean the branches are cut up to 6 meters high. And as the trees grow out wider, they layer on sapwood that is clear and without knots. That means that when we sawmill these logs, we get clear timber without a lot of blemishes. And that means, once again, that it's suitable for wood modification technology. I can imagine one of the first things you're thinking about is, that's great, Daniel, but New Zealand's a long way from Europe and the UK, and that's true. But the way this tree grows and the way that we process it means that even with 21,000 kilometres of sea freight, the timber is still storing a considerable amount of carbon. In the case of sawn, thermally modified New Zealand radiata pine, or the Obodo product, we're still storing 535 kilograms of carbon per cubic metre, or carbon equivalent per cubic metre. And that's all in our Environmental Product Declaration, or EPD, that Steve's just popped in the handout. So you're welcome to have a look at that. It's not just important, of course, to have sustainability only. You need to provide natural beauty and durability with timber, particularly when it's being used outside or in feature type applications. And we use two technologies to achieve that at Obodo. The first base technology is thermal modification. Most of you will be familiar with the Thermowood brand. It's been around for sort of 20, 25 years. It was originally developed by the Finnish, really, in a commercial sense. And what that does is heats the timber at a very high temperature and alters the cellular structure of the wood to create a situation where it can absorb less moisture and hold less moisture, thereby reducing the equilibrium moisture content and improving the stability and the durability of it. And I'm sure Callum will talk a bit more on the different types of modification that are available in the market today. When we thermally modify, we use a special type of kiln that goes up to 230, 240 degrees. These are the ones that we use in New Zealand. Obodo is really the only scale producer of modified wood in the Southern Hemisphere. And we're producing, in the case of thermally modified wood, we're producing about 15,000 to 20,000 cubic meters per year. As I said, the process alters the cellular wall, and this is a very simplified drawing, but what you see is that cell wall having its ability to store moisture reduced. And the resultant product is a very consistent chocolate brown. It is class 1 durable under the EN 113 standard. It is considerably more stable, and the thermal properties are improved by about 20%. Now that makes it great for applications like window joinery, where thermal conductivity is an important aspect to consider. It's not just about thermal modification. About is a secondary process called grain orientation, and this isn't new technology. Grain orientation has been recognised for a very long time to be an important technique to improve the weatherability and the performance of timber in an outside application. Traditionally, you've probably heard of species like quarter-sawn oak or quarter-sawn western red cedar or vertical grain western red cedar. It's been known for generations that the way we orientate grain has a massive effect on the way the timber weathers. And those two effects are summarized as A, increasing the stability and service. So you can see in the sketches here that there's less expansion across the face of the board if the grain is vertical. And B, surface checking, the amount of cracking you receive on the face of a vertical grain board is less than a flat sawn or a plain sawn board. And at Obodo, we actually engineer the grain. So we take a flat sawn board, we laminate it into a large block or a flitch, and then we slice that to the dimension that the customers need. The resultant product is available in very large sizes, and we're talking sizes up to sort of 200 by 300 or 200 by 400, and it can be sliced down with a bandsaw into dimensions that are required by the market. And the benefit of that is, of course, flexibility from design. If you're a designer, you can get a small 2x2 batten up to a 300 by 300 post in a very stable timber and a very consistent application. And you get that beautiful vertical grain aspect that you can see there in the image. Our flagship product for Europe is our Vulcan vertical grain cladding, and that's a high performance, very stable vertical grain product that's engineered vertical grain. It's available in a range of profiles and finishes, and it gets the sort of natural, clean aesthetic that you would see primarily from old growth species like, for example, cedar or Alaskan yellow cedar, those sorts of clean, lightweight, stable softwoods. It will accept dark colours and take the heat in challenging applications, and you'll get that natural brown colour. A secondary or a sort of a second level product that we offer is the same cladding but in a flat sawn grain. The main benefit of this is it's more economical, but it also has the durability and stability that you would normally see from thermally modified wood. Similar profiles that are available, but the aesthetic is a little different. This is a barn conversion in the UK, but you'll see the grain is a lot more flat and open, which has a different sort of aspect to it. The house in Scotland, similar profile. Of course, this sort of wood is very suitable for charring, and I know that there's been sort of mixed results for charred wood in the UK and Europe, but there are some operators that are doing a very good job. There's a company called Swarthout in Holland that buys this product here and chars it, does a very good job, and they're distributing product throughout Europe, and it's also available in the UK through our distributor Glenarm. So that's certainly a cost-effective substrate and a stable substrate for charred wood. One thing that Obodo is a little bit different on is the fact that we take a sort of a whole solution, a holistic solution when it comes to designing products. And we don't just stop at the timber. We also have designed and offer a tested coating system that works synergistically with our wood. And the purpose of that is giving a user experience that is consistent. There's many problems where people will purchase a wood product and then go and purchase a coating, say from B&Q or wherever, and end up with a terrible result, where what we provide is a tested system of coatings and wood that are guaranteed to work together and give you a consistent performance. We've also gone to the point where we've developed our own end seals to seal the end of the wood and colour match with our coating, so that we have critical failure points like end grain well sealed in a system rather than just a kit of parts approach. Protector oil is available in a range of colours, darks, lights, and we've got over 6 years of history weathering these, so we can tell you what they're going to look like over a period of time, and we can back that up with time-lapse videos. So you've got a lot of peace of mind on what this product is going to do over a period of time. And if you're designing, you can design a house and predict relatively accurately what it's going to look like in 2, 3, 4 years' time. The product's also suitable for these sorts of ceiling, feature walls, sophites, semi-exposed applications. This paneling here you see is only 10 millimeters thick, so it's quite a cost-effective way to clad ceilings and sophites. As I mentioned earlier, it's available in flips that can be ripped down into many different sizes, and this gives you a whole lot of flexibility. This here is a feature balustrade designed in New Zealand. You're talking about screening and brise soleil, even large sections. This is a library in Wellington, New Zealand, and the architects have designed a 600 millimeter wide fin, which has been CNC detailed using a native Maori design that the architects chose to use. So there is really no end to the flexibility of this product based on the way that it's engineered. Is it Queen Victoria Park, Steve, in Melbourne? Is it? Yeah, so this is in Melbourne City, but it's another example of our screening being used. We've also got a decking offer for Europe. It's a mid-market product. It's quite cost effective, and it's available in your standard sort of profiles you'd see in the UK and Europe. This is a great solution from a price point of view because it's cheaper than a premium hardwood, but it's also got that rich brown natural aesthetic that you would achieve from a hardwood, and it's cheaper than a hardwood, more expensive than a pressure treated piece of pine. So it's what we think is quite a good value proposition for the market. In terms of availability, our product is stocked with 3 companies in the UK. We've got our master distributor up in Scotland, Glenarmon Timber. They're vastly experienced in dealing with our product. They manufacture, mold, and coat the product in the UK. They have the ability to finger joint the product up to 12 meters. I think if I've got that right, and CNC cut the product. And also stocking distributors Norclad in Bristol, and Millworks in Cambridge and Swindon. On the continent, we've got Plastica in Holland, Van der Kasteel in Belgium, Froslev in Denmark, Kurtz KG in Germany, and Ravioli Lignami in Italy. So we've got a good portion of the market covered with stocking distributors. So it's a fairly accessible product. That's about it from me. I wanted to keep that short and sweet. Look forward to hearing from you, Callum.
Thank you, Dan. Just before I hand over to Callum, what I'm going to do is I'm just going to share a poll. So just if you're wanting to learn a little bit more about the company, or if you do want some small little samples or something like that, just hit one of the options in the poll. That'll give me your details. Doesn't matter what country you're from, and we will get in touch with you. We will, whether you're wanting links or whether you're wanting samples or that kind of thing, just hit us up. Or if you're wanting you have a few more questions, keep those questions coming in. I'm highlighting them and we'll answer them at the end. I'll just change this over and I'll switch it over to you, Callum.
Okay. Am I live?
Yep.
You can hear me. Okay. Well, good morning from North Wales. It was very nice and sunny until 3 hours ago, and now it's back to normal Welsh weather. Yes, I'm Callum Hill. I'm the CEO of a consultancy called JCH Industrial Ecology Limited, which is a bit of a mouthful, but it's actually a name that I chose because it's something I believe in, industrial ecology. I'd be delighted to talk to you about sometime. One of the things that it's concerned with is measuring materials flows, and I'll be talking today something about carbon flows and how timber can be used as a material to sequester and store carbon in long life buildings. So I've just pressed the button and absolutely nothing's happened. So
if you just click across to the next one on
I have done that. I have done that. It's not happening. Okay, well, I'll just press. That's all right. It's okay. It's just it worked on the button before, but now it isn't. So it worked perfectly in the rehearsal. So why modify wood? Well, wood's a fantastic material. There's no doubt about it. I've been using it for thousands of years, if not longer than that, hundreds of thousands of years. But it does suffer from some disadvantages. Hygroscopicity, a bit of a mouthful again. It's susceptible to moisture, and because of that, you have properties like dimensional instability, some species being worse than other. Plantation grown species are a bit notorious in that respect, so even if you have old growth timber which is reasonably dimensionally stable, you tend to find that the plantation grown timber isn't as good. We have this thing called mechanosorptive properties, which basically means the mechanical properties of the timber change as the moisture content changes, and that can present challenges if you're using timber in structural applications. Durability, of course, it's susceptible to mold, it's susceptible to fungal attack, it's susceptible to insect attack, and then there's the famous weathering of wood, where people have tended to throw their hands up and say, well, it develops this wonderful driftwood grey appearance, but in reality, when architects take pictures of buildings, it's usually 2 weeks after they built it rather than 2 years down the road. So is there anything we can do to, if not completely remove these negative properties, at least ameliorate them? And that's really where wood modification came in. I became involved with wood modification in 1994, which is quite some time ago now. And about 2 years after that, we formed something called a thematic network in wood modification. It was a European-wide network. And at that time, there was only one wood modification that was commercially available, and that was the Finnish thermal wood process. But actually, wood modification has a very long history. I think the first paper I've seen about thermal modification is dated 1911, and that's from the Forest Products Lab in the United States. The first acetylation paper I'm aware of is something like 1935, and looking at resin impregnation and things like furfuration, we're talking about the late 30s, early 40s. So this has got a very, very long history. So basically, the basic definition, because one of the things that we had to come up with in the thematic network is what is wood modification? And it was usually considered to be some chemical change to the wood. So either you thermally alter the wood so that the chemistry of the wood's changed, or you perform a chemical reaction on the wood so that you have introduced new functionality into the wood. But we also became aware during the time of the thematic network that there were people working with resins, phenol formaldehyde, melamine urea formaldehyde, and of course furfuration. And it's not entirely clear where those sort of modifications fit. So we introduced a term called impregnation modification. People tend to get rather obsessed by hydroxyl groups in wood and what they do. And it's always assumed that there has to be a reaction with a hydroxyl group for modification to work, and that isn't actually true, as I'll show in a little while. So what's happening to the wood is happening at a cell wall level. And this is just a picture of a piece of pine taken with a scanning electron microscope. These cell walls are very small. They are visible with a hand lens. If we go further into the cell wall, that structure of the cell wall is made up of polymers. The main functional polymer is the cellulose, which forms these lines that you can see on the drawing here. Between those cellulose molecules, there are other molecules called hemicelluloses and lignin. And it's that area where the modification takes place, in the spaces between the cellulose, essentially. And to simplify what's going on, the lines here again represent the cellulose, and between those cellulose molecules, there is the potential for water to be absorbed because of the presence of these dreadful things called hydroxyl groups. When the wood dries, the water goes out, and that space, basically the wood collapses in that region, And so you get this dimensional instability, this shrinking and swelling of the wood. When you resaturate or re-wet the wood expands again. So we get this dimensional instability. So it's this attraction between wood hydroxiles and water molecules that's responsible for that. And if we could do something to get rid of these pesky hydroxyl groups, our life would be so much better, of course. One way of doing this is to perform a chemical reaction. As I say, a lot of the original wood modifications were concerned with performing a chemical reaction with these hydroxyl groups and essentially eliminating them. And this is the basis for acetylation. You react the wood with acetic anhydride. The acetyl groups occupy the space where the hydroxyl groups were. Because the acetyl groups are bigger, they occupy a lot more space. And that space would normally have been occupied by water, either liquid water or sorbed moisture. And that space isn't there anymore, it's filled up. So that gives you the dimensional stability. It means the wood stays a lot drier than it would if the acetyl groups weren't there, and that gives you the fungal decay resistance. So although the hydroxyl groups are involved with the reaction, it's not directly the removal of the hydroxyl groups that gives you the properties. It's more the filling up of the space between the regions, the cellulose regions, that give you this property. So acetyl groups, you naturally find them in wood anyway. Acetylation just increases their concentration quite considerably. At the moment, this is the only chemical modification that I'm aware of that is available commercially. And of course, the Acquia product is pretty famous now and has got a lot of devotees because of its high quality properties. The only thing that you have to note is that during the reaction, acetic acid is given off as a byproduct, and that acetic acid has to be removed from the wood. I remember going to an acetylation plant many, many years ago, and rather foolishly walked around, saw a stack of timber with a plastic bag over it, which should have given me a bit of a clue. But I lifted the plastic bag and gave it a good long sniff, and I nearly died because of the smell of the acetic acid. So I learnt a lesson that day. Of course, the stuff that's produced commercially, they remove the acetic acid first. You may get a little bit of residual, so you should always use stainless steel fixings with this type of wood. So Titan Wood, as they were known, they produce this product called Acquia, and there's also the Tricoya product, which is wood chips that have been modified. So I think they're increasing production to about 80,000 cubic meters of solid wood. And quite soon there'll be a plant coming on stream in Hull in the UK, which will be producing acetylated chips for MDF. Okay. So the next modification I'm going to talk about is impregnation modification. This uses monomers that are impregnated into the wood and then polymerized within the wood. These monomers may or may not react with the hydroxyl groups of the wood, and it doesn't really matter whether they do or not. The basic idea is that you're filling this space between the cellulose molecules where the water would like to go. The problem is that if you just fill that space up with a water deliverable system, which is what is used for the impregnation modification, if you don't polymerize it, when you put the wood back in liquid water again, those molecules will come out and you lose that ability to bulk the wood, to deny that space to water molecules. So in order to get around that problem, after the impregnation, you polymerize the wood, polymerize these monomers. The polymer itself may be bound to hydroxyl groups, which I've attempted to show in the diagram, but it's not necessary. People get a bit overexcited about whether or not they've reacted with the hydroxyl groups. The most important thing is, does it leach out after you've done the polymerization reaction? And if it doesn't, it's fit for purpose. That's the most important thing. Does it do the job? There are a number of examples of impregnation modification. Some of them claim to have reacted with the hydroxyl group, but as I say, it's a bit of a waste of time having this debate because it doesn't really matter whether it does or not. The important thing is whether it works. So Kerbony's been around for quite a while. He's a picture taken with a microscope, fluorescent microscope, that shows the presence of the furfural monomer and then the polymer after the reaction, which is in the cell wall, which is where you want the stuff to go, so it can do the job that you expect of it, which is denying the space to water molecules. There's an example of a building up in the Highlands of Scotland, which uses Kebony cladding. And the other one, sort of the new kid on the block, it's only been around a little while, but more than a year now, I think, is the Lignia product, which uses a different kind of resin. And this is getting a lot of devotees as well. So I wish them well in the future. And then we come to thermal modification, which is the subject of the talk we had before. This involves heating wood in the absence of air, temperatures exceeding 180 degrees centigrade. So you always get a color change. You're sort of caramelizing the wood. You tend to get this sort of caramel smell associated with thermally modified wood. So you get the color change. You get a loss of strength. This is more an embrittlement of the wood. The issues that the thermal wood processes used to have in the old days, as I say, when we first started with the thematic network, there used to be some issues about machining, but I think they've really got that under control now. So you get a very nice finish with thermally modified wood when it's planed. It can be finger jointed. It does tend to be brittle, so you don't bang nails through it. You have to have the recommended fittings for it. Drilling is always recommended if you're going to screw it, but you can get fittings which are specially designed for working with thermally modified wood. And what you're basically doing here, you're taking the polymers which are responsible for the water sorption, which is primarily the hemicellulases, and you're degrading them. You're breaking them down. You're converting them into other types of polymer which are a lot less susceptible to water. You get mass loss associated with thermal modification, so because the polymers themselves are actually being converted into volatile components which are removed during the process. And you also may or may not get some cross-linking. So there are still hydroxyl groups left. So there are hydroxyl groups left with acetylated wood. There are hydroxyl groups left with impregnated wood. So you get some water absorbed into the wood. So you get some of the properties of the wood. You get some dimensional instability, but compared with what the wood's like in its native state, it's pretty insignificant. But it does need to be taken into consideration during the design process. You can't butt even thermally modified wood up right next to each other and not expect there to be some expansion and contraction, so you have to be aware of that. But compared with native wood, the dimensional instability is not very significant. Okay, so I've only got one example of thermal wood because I thought Bodo would appreciate having the name on here. A very nice product it looks like as well, I have to say. So I shall be putting my name down for some large samples so that I can make a nice bit of test decking around my house. So we'll talk about that afterwards. Right, so the main purpose of my talk today is to talk about the environmental product declarations that have been published for modified and unmodified woods. I've restricted myself to solid wood. I haven't looked at composites, and I haven't looked at things like glue lambs, cross lambs, things like that. So we're looking at solid wood only, and we're looking at modified and unmodified woods, but a little bit about what an environmental product declaration is. They've got a lot of publicity now. I think everyone's heard of environmental product declarations, whereas a few years ago no one had. The problem in LCA, with LCAs and in the LCA community, is that people tended to do it their own way. They tended to use their own impact indicators. And there are always variations between the methodology. And what the EPD is a way of making sure that everybody follows the same rules. And these rules are published by something called a program operator. In the case of the Aboda one, I think it's the International EPD system, who have a kind of a branch office down in the Southern Hemisphere. It's a Swedish-based system. What they're trying to do is to make sure that the EPD program operators also follow common rules, because what did happen was that they all went off and developed their own rules independently of each other. But now these are being brought together under different standards. The most commonly used is the EN 15804 standard, which is in its third iteration now. And it's aligned with something called a product environmental footprint. The whole business of doing LCA, EPDs, environmental footprinting is full of acronyms, half of which people have never heard of, including the people that actually say what they are. The important thing about an EPD is that it's not just an LCA that's been done by a company and says, isn't our product fantastic, buy our product. It is subjected to a third-party independent review, and these independent reviewers are entitled to go, hold on, where did you get that number from? I need to see the calculations. So it's not a free-for-all, basically. These rules are there to allow comparability between EPDs. That's the idea. Unfortunately, it doesn't always work in practice, but it's getting a lot better than it did, certainly since the introduction of the EN 15804 standard. So here we have an environmental product declaration for the Obodo product, and what Obodo asked me to do was to go out there and just see what's published at the moment. There have been some that were published quite some time in the past. They have a lifetime, a finite lifespan of 5 years generally. And then things move on, things change, like grid mixes change, people change their processes. So these things get updated as time goes on. So it's always important to be aware that you're working with the current version, not a version which is no longer valid. So there are a number of impact indicators that are looked at in environmental product declarations, which are covered by the standard. Some of them, quite frankly, are controversial, and it's actually got a bit worse since the latest version of EN 15804 has come along. I'm not going to get involved in that debate. I'm only going to be talking about global warming potential and embodied energy and inherent energy, which I'll explain in a minute because people always get them mixed up. Global warming potential is one of the indicators that we are extremely confident is accurately represented because we understand the science well. There are other indicators which are produced in EPDs, which the science isn't so well understood, and there is still debate as to how these things should be calculated. But that is not the case with global warming potential. It's not the case with embodied energy, and it's not the case with the inherent or the energy that's actually in the material, which is what I'm talking about today. So a quick explanation of what global warming potential is. We have a number of processes that go into making a piece of wood. And this goes all the way back to, if we're using electricity, we have to generate that electricity from primary energy sources. Depending on the type of energy source that we use, we have different emissions. If we were burning fossil fuels, we'd have much higher emissions than if we use solar energy. But if we're using solar energy, we have to make the solar panels, and that takes energy to do that, and there are emissions associated with that. So we have to take everything back, right back to nature, essentially. How do we get things from nature, process them, use them to create the things that we need in order to make the timber product? So it's a very long chain, causal chain that is involved when you're doing LCA. All these things have emissions associated with them. Some of these emissions might be historical emissions and some of them are current emissions, but we have to take account of them. We have to take account of them properly. So you will see in products that some have different global warming potentials for what seems to be the same type of product. And the reasons for that are generally related to, well, what was the grid mix, how much transportation was involved. There may be subtleties with the process. Maybe they used biomass for kiln drying, somebody else used diesel oil. These sorts of things can lead to differences in the global warming potential. You need to be aware of this when you're trying to compare products. The sequestered carbon is a lot simpler, of course. As trees grow, they absorb atmospheric carbon dioxide. The carbon in that is stored within the wood itself, and it will remain stored in the wood for as long as that wood is used in products. At the end of life, we might incinerate that wood. We would recover the solar energy that's stored in that wood and hopefully use that to in some process, maybe generating electricity, but that carbon dioxide would then be returned to the atmosphere where it's available for new growth subsequently. So if you look at an EPD, and I recommend that you do because they're fascinating reading, If you look at the latest versions, you will see figures like this: global warming potential total, global warming potential fossil, global warming potential biogenic. And the rules for how you report these are in the standard EN 15804, and I'm not going to go into the details, but essentially we have positive and negative numbers here. The negative numbers are because of the sequestered carbon, which we call the biogenic carbon. The positive numbers are the emissions, the things that were maybe to do with generating electricity, making the equipment that was used to process the wood, the emissions associated with transport, that sort of thing. So those are all recognised as being positive, and negative is where things are removed from the atmosphere. So storage is negative and emissions are positive. And you see, if we subtract the positive from the negative, we still have negative, and that's an important result, which I will emphasise at the end of this talk. We have carbon negative materials when we use timber, so we can use timber excuse me, as a way of storing atmospheric carbon and as a mitigation measure. So that's the global warming potential, the total figure, which is negative, and the fossil, and the biogenic. Now the embodied energy is a little bit trickier. The embodied energy, the units, all the units have been per meter cubed of product, which is called the declared unit in EPD. The units of the embodied energy are megajoules per meter cubed. The embodied energy is the primary energy that's been used in the processing. And people often make mistakes, and they assume if they read the meter at a sawmill, that was the energy that was used, that is the embodied energy. That is not the case. The meter is reading the electricity that was used, but that electricity had to be generated, and that electricity had to be generated from primary energy. And it's the primary energy that we're concerned with when we look at embodied energy. So we have to take everything back to nature, the source. What was the source of that energy? Was it solar? Was it nuclear? Was it hydro? Was it biomass? Or was it a chemical energy of some form like fossil fuels? I basically ran out of icons. That's why you've got a little thing, beaker there with some bubbles coming out. So that represents fossil fuels in this case. And it can get complicated. There are debates about, well, how do you represent solar energy? How do you represent nuclear energy? It's not always very clear how you do that. So because of that, sometimes embodied energy can be over-reported or under-reported because people might not be using common calculation rules. It shouldn't happen, but it does happen. So reading an EPD and trying to work out how you get embodied energy is not that straightforward, because you have these dreadful terms. I don't know who chose them. Renewable primary energy is energy carrier. Renewable primary energy resources is material utilization, and total use of renewable primary energy resources. What the hell does all that mean? It's not that obvious. So if you want to know the embodied energy, you have to look at the energy carrier entries. And we have two here. We have the non-renewable, which would be the fossil energy, and we have the renewable. So these are very important numbers. It tells you how much biomass has been used compared with how much fossil fuels have been used. You can see in this particular EPD, I'm not going to embarrass anybody by saying which one it is. Clearly, they're using a lot more biomass for their energy purposes than they are using renewable, non-renewable primary energy. So my guess would be that this is probably coming from New Zealand, but I'm not going to say who this is. But these are important pieces of information. So if you want to work out what the embodied energy is, that's where you look in the EPD. If you want to know what the inherent energy is, also called embedded energy, which then starts confusing everybody, including myself, because it's so easy to say embedded when you mean embodied, and embodied when you mean embedded. Stick to inherent energy. Energy is what's in the wood. If you burn a piece of wood, you get energy out of it. That's the inherent energy. It's an important number because at the end of life, end of product life, or several products, if you cascade this down through the life cycle, if you're sensible, you're going to recover that energy, and you're going to use that in a biomass energy plant. But it makes a lot more sense to have stored the carbon for a long period of time in a product before you burn it. There is a debate going on, which again I haven't got time to talk about, regarding the use of biomass directly in power stations compared with cascading it down through product life cycles and using it at the end. It makes a lot more sense to use it at the end rather than at the beginning, obviously. It is obvious, but there's still a debate about it. So if you want to know where that number is, that's the renewable primary energy resources as material utilization. If you were to look at further down, there's one that says non-renewable primary energy as material utilization. If you had a plastic component that has energy in it, but it's a non-renewable primary energy resource, you could recover that energy through incineration, and that's why it's reported. But for this product, because it's a timber product, it doesn't have any plastic in it, it just has renewable primary energy. So that's the inherent energy. So those are the numbers that you use from the EPD to do the analysis. And what I've done here is I've looked at the embodied energy, which is the energy that's gone into the primary energy, it's gone into making the product. And I've looked at the global warming potential associated with that. And you should have a relationship between those. They're not going to fall on the same line for the reasons I mentioned, because it depends how the primary energy, what the grid mix was. It depends on subtleties of the processing. It depends on transportation, many other factors. But basically, we do have a clustering, and we can draw some sort of linear relationship between there. And as you would expect, as the embodied energy goes up, so does the global warming potential, although there are some notable kind of outliers on this particular graph. I don't really have time to go into the reasons for that in this talk. So having divided this up into modified and unmodified solid wood products, we're looking here at the green products, the dried products, and the sawn and plain products. What we should see as we are increasing the amount of processing, we should see the embodied energy go up, but the relationship's quite loose. As we get more data, I think we will begin to do some statistical analysis on this. But there are, as I say, because embodied energy is measuring the primary energy, there are factors such as what was the grid mix, which can be a very important consideration when you're trying to analyze these things. So it's not totally simple. We're also seeing very high GWPs with some of these products, even though they have quite low embodied energies. And the reason for that would be, you would expect that there's a very high fossil component to the grid mix in this particular case. As grids decarbonize, these numbers will go down. It's unlikely the embodied energy will go down as significantly, but the GWPs will certainly go down in the future. So then we come to the thermally modified wood, and we can see the Vulcan wood. The numbers are clustered around about between 200 and 300 kilograms carbon dioxide equivalent per meter cubed, and the embodied energies are sort of between 5,000 and 10,000 megajoules per meter cubed. I don't want to get into some sort of top trumps thing here about who's got the best one in terms of embodied energy. It's a pretty pointless exercise when you're trying to compare one timber product with another. We're really more concerned about the carbon dioxide emissions and getting those down. And as I'll say, emphasize at the end, what we're really concerned about is, does the sequestered carbon, is more sequestered carbon stored than carbon dioxide is emitted due to the processing? Does that make it a carbon negative or carbon positive product? If I start comparing with steel and concrete, we'll be here all day. But suffice to say, these numbers are not, they're not bad numbers, basically. And then we have the chemical modification. I haven't got one for lignia yet. I understand they are producing an EPD, but it isn't out yet as far as I know. We've got 3 for Accoya, 3 for Kebony. Within there, we have the radiata pine products. My understanding with Accoya is that the commercially available product is based upon Accoya, is based upon radiata pine. I've had quite a lot of experience of doing impregnation modifications, and I have to say, sort of an advert for radiata pine, it always comes out best. It's easy to impregnate, it doesn't distort, and it always looks good. There you are, an advert for radiata pine. Other species are kind of playing catch up. A lot of it's down to, because it's fast grown, it's very porous, and because of the management that was mentioned, you don't get many knots. I don't remember ever seeing one in a piece of radiata. And that really helps when you're doing modification, and that includes thermal modification. So moving on to the next slide, this is the radiator-based products. So I'm trying to compare like with like here. I should say that I'm only comparing what are called modules A1 to A3, which is the cradle to factory gate. I haven't brought these together to include transportation, but the transportation, you tend to find the big impacts come from lorry distances when you've got big ships chugging across the ocean. They tend not to have phenomenally high emissions associated with them, but I'm not comparing that in this particular graph here. So this is all cradle to gate, so I'm looking at process emissions only. The Kebony has the highest emissions and the highest embodied energy, but this is related to the fact that you have to produce the chemicals and the processing itself does take energy. Now, it doesn't mean that Kebony is worse than other things, because all we're looking at here is cradle to gate. We're not looking at the whole life cycle. We're not looking at things like life extension, maintenance cycles, this sort of thing. So you have to take those into consideration when you're making materials choices. The Accoya sits a little bit lower, but again, I'm not going to get into this debate about, oh, our product's better than your product, because it's not that simple. It really isn't. Excuse me. So the energy, we have the embodied energy, which is how much energy it took to make the product, and we have the inherent energy, which is how much energy or solar energy stored in the product. And you'll notice that as the amount of processing that you use increases, this is purely for the radiata pine products again, you'll notice that the embodied energy increases. The embedded or the inherent energy should be roughly the same for most of these products. It's slightly lower for Accoya. That's because we're measuring per meter cubed, and the Accoya swells when it's acetylated. So the meter cubed of Accoya contains slightly less radiata pine than the meter cubed before it was acetylated. So I think that's the reason why the inherent energy is lower, but I'm not entirely clear about that one, to be quite honest. The Kebony is much higher because you have the furfural polymer also has energy in it, which can be recovered when you burn the Kebony. So with some of the products, if we look at the less processed products, you'll actually see the inherent energy is higher than the embodied energy. So you've actually got not just a negative carbon, but also a negative energy material. The important thing is that you can recover the energy in the life cycle. You can't do that with non-renewable materials. So this is an important part of the consideration, because you have this substitution effect as well, because you might be substituting for a fossil fuel. And here we're looking at sorry, I think I got that wrong. We're looking at embodied and inherent energy. I don't know what's going on there. I'll go back to that one later on. Oh, no, it's all right. No, just ignore me. The trouble is, every time I press a button, a big thing comes up in front and I can't see what I'm talking about. This is the thermally modified. So again, we're having the embodied energy varies quite a lot actually between the different thermal modifications. I'm not sure why that is. Perhaps the manufacturers would like to contact me and tell them something about their process. We might be able to help them get their embodied energies down. The GWPs weren't necessarily increasing because of this. I'm not quite sure again why that is, because I don't have the essential details of the process. Here's the important one. What's it going to do for global warming? Now, every single one of these products has got a higher stored carbon compared with the emitted carbon. These are measured in GWP carbon dioxide equivalent. So that carbon is being reported as the same unit. Each one of these, you will see the blue line is higher than the red line, which essentially means if we take one from the other, we end up with a negative number. There's the thermally modified products. These were the radiata pine products. That's what we end up with, just for the thermally modified, but you get the same for all of those products. In fact, you get the same for all timber products. You end up with a negative number. Now, there is a bit of complication here, which again, I don't have time to go into, in that eventually, of course, that carbon is going to come out, but when we're doing that, we're going to recover the energy. We're going to substitute for presumably a fossil fuel. So although that carbon will come out, if you store it in a long life product, you can be pretty sure that that carbon is not going to come out probably for 100 years, possibly longer. If you use modified wood, they have much longer lifetimes anyway. So although the impact's higher using modified wood, the storage time is also longer. I'd be delighted to give another talk about how that affects storage time and the carbon flows another time. But I think I've probably talked enough and probably confused you enough. But I hope you got something out of that. Here's the take-home message on this slide anyway. Thank you for listening.
Thank you very, very much for that, Callum. Yep, that was the last one. Okay, we have a few questions. Let me just go to those. Can we get a copy of this presentation? This presentation is going to be available for rewatching. Callum will actually be putting it on his own website as well, so you can head over to his own website. Someone asked a question about bamboo products. This is probably the wrong presentation for you. Sebastian asked, does your protector prevent weathering / silvering? And then part 2 is it fire tested with certification for compliance in the UK? That's probably for you, Dan.
Yeah, okay. Hi, Sebastian. Does your protector prevent weathering? The answer is yes. And, it comes down to your choice of final aesthetic. So our protector oils are available in a range of different colors, and you would choose the color that you want up front. So if you wanted a dark brown color, you'd apply that, and you'd be recoating, arguably anywhere between every 3 to 5 years to maintain that brown color. If you wanted a silvered color, you'd start with a lighter gray tone like patina, which is one of our colors. You'd apply that to the wood, and then you would see the wood silver off in a controlled manner. And one of the benefits of coating with a light gray is that you'll keep the wood looking fresh, and you'll minimize the chance of fungal decay and mold and discoloration on the product as it weathers. So it's very much about the final aesthetic that you want, and then choosing an appropriate color and a maintenance schedule to maintain that color over a period of time. Yes, we do have fire testing for the UK. We can provide you some information on that. That's the Eurocode B certified system that's available through Glenarm Timber in Scotland. So yes, I guess to that question. Hopefully that answers it for you.
Awesome. And now the first question of part 1 kind of flows onto the next question, which we got was obviously with regards to, sounds like Catherine's got a couple of projects that she's wanting to silver off. So you just want to go over the patina or...
Yeah. So Catherine, there's 2 options there really. You can choose a pigmented silver grey like our patina to get an even weathered grey. That's option 1. Option 2 is to go to a silicate type weathering coating like CU or CUX. Now that does create a weathered grey look, but it doesn't do it with a pigment. It does it with the surface reaction on the timber over time. So you could use either one of the 2 to get a result that will give you the weathered grey look that you want. The silicate coatings like CU would probably give you a longer recoat period compared to a pigmented coating, but it comes at a higher price. So you just want to work out what your options are and look at both of those options, and we can provide you with time-lapse videos of how these coatings are going to weather over a 24-month period. You can get a feel for what they're going to look like over time. So that's information that we can give you.
Awesome. And then there was just another question that came in examples of use in railway stations. Are you from Felicity? Are you referring to timber in general, or our products in particular? I don't know. Have we done any railway stations?
Not that I know of. In New Zealand,
Product. Okay.
done a pretty poor job of keeping our railways going. so we don't have much of a railway left, to be honest. So no, but there's certainly infrastructure projects around that may be relevant. So it's really just getting a feel for what your design is and what you're trying to achieve, and then we can possibly provide some reference projects that would be relevant.
Yeah, no, absolutely. Get in touch. I know here in Australia, my colleague and I, we've worked on many railway stations in general over the years. So definitely drop us a line. I'm more than happy to help out and work through some concepts.
Yeah, toxicity, I can answer that one too, Felicity. Well, it's thermally modified wood in general is about as toxic as untreated wood. So yeah, there's no additive added to the product during the process. Callum, do you have any comments on whether thermally modified wood would be more toxic than untreated wood?
You do get some generation of extractives that aren't naturally present in the wood, and it depends on the process, because some processes they do a pretty good job of cleaning up. You will notice a smell, that's for sure, and with some products it's stronger than others. I wouldn't necessarily claim these things have inherent toxicity. That's pushing it a bit.
Yeah. I mean, you wouldn't eat wood, and you wouldn't eat thermally modified wood. But I think you'll find, generally speaking, and from our product point of view anyway, you wouldn't see our product being any more toxic than untreated timber. Generally speaking. London Underground stations. I wouldn't see any issues there at all from an application point of view or from a VOC point of view. And we've got published VOC stats for all our finishes, so we've kind of got that covered up.
Cool. There weren't any other questions that came in. Did you have anything else to add?
Not from me. I don't know if you've got anything, Callum.
No, I don't think so. No, other than to apologise that I didn't read my graphs when I was talking and confused myself, because as I said, this box came up that I couldn't see what's behind it. So apologies for that.
Oh, this is a big one. What about the Shosuki band treatments?
Yeah, I can answer that one, Grace. I mentioned earlier there's a company called Swarthout, I think is the correct way to pronounce it. They're in Holland. They do a very good job of Shosuki ban or charred wood. It is quite a simple process, but it's very easily done ineffectively. And what we find a lot of the time is it's very easy to run a gas torch over the wood and make it black. But to really get a good result with Shosuki ban is you actually require a 1 or 2 millimeter thick char layer on the outside of the wood, and you've got to choose the right timber. So, I mean, my suggestion would be to talk to, if you're based in the UK, I would talk to Glenarm Timber. They work closely with Swarthout in Holland, and they certainly do a very good job of providing legitimately charred wood for a long-term performance, and they're very much masters of that process. So I'd reach out to Glenarm Timber, and they will put you in touch with Swarthout in Holland. That's my tip.
It is something which we're seeing a lot of people getting wrong here in Australia. There is an art to it, so make sure you do your research. It's beautiful, but do your research. Fantastic. We'll wrap it up there. No more questions. Thank you very, very much, Callum, for taking the time out. It was a very interesting presentation. It will be available. And thank you, Dan. It's very late compared to me here in Sydney. I mean, I know it's a 2-hour difference, but still. Cool.
All right. Thank you very much. Thanks for coming, guys.
Thank you.
Cheers. Bye-bye. Thanks.